In part 1, we said AI has moved through 3 eras: handwritten rules, then statistical learning, then deep learning. Here's the question that era shift actually answers. Instead of a human writing thousands of rules by hand, what if you could just show a machine some examples and let it work out the rules for itself? That single idea, learning the rule instead of writing it, is called machine learning, and it's what this entire video is about. Welcome back to the Artificial Intelligence Institute Africa, Aiia, Ubuntu Guild's videos on AI. I'm Dr. Dennis Magaya, Chairman, AIIA. This is part 2 of our What is AI series. We're assuming you've watched part 1, which is the 4-part definition of AI, and the 3 historical eras are prerequisite knowledge here. Before we dive into the details, let me show you the road ahead. We are covering 3 layers today. Layer 1 is the core definition, what machine learning actually is, and the simple loop that makes it work. Layer 2 is the landscape, the 3 main paradigms of machine learning, distinguished by how they learn and what kind of data and experience they use. Layer 3 is the big picture, how deep learning fits inside machine learning and how machine learning fits inside AI. Layer 1 is your foundation. Layers 2 and 3 are your map of the territory. Let's start with Layer 1. Recall the second of Part 1's 3 eras, statistical learning. Machine learning is the formal name for that era's approach. Rather than a human hand-coding every rule the way symbolic AI did in the 1950s, a machine learning system is shown data and given experience, and it works out the underlying pattern itself. Machine learning is a subset of AI in which systems improve their performance on a task by learning from data and experience, rather than by following explicitly programmed rules. Said even more simply, instead of programming the rule into the machine, you give it enough data and experience through examples, exploration, or trial and error that it can figure the rule out on its own. Here's the mechanism underneath that one sentence, and it's a loop, not a single step. First, the system makes a prediction based on its current, usually very rough, internal settings. Second, it compares that prediction against the correct answer, producing an error, how wrong it was. Third, it adjusts its internal settings slightly in the direction that would have made that error smaller. Then it repeats thousands, sometimes millions, of times over many examples. Think of it like an elephant calf learning to find water in a dry riverbed. The calf knows it needs water, but it doesn't know where to dig. It tries one spot, too dry. It tries another, still no water, but each time it learns something. The soil here is too sandy. The vegetation there is too sparse. Slowly, through repeated trial and error, it learns to recognize the signs. A patch of greener grass, a certain type of tree that signal water is near. That's machine learning mechanically. No one explained the geology of the riverbed in advance. The calf inferred an increasingly accurate map of where to find water, purely from repeated feedback and experience. Say it back in plain words. A machine learns by guessing, checking how wrong the guess was, nudging itself to be less wrong next time, and repeating that cycle enough times that the guesses become genuinely good. Recall Part 1's first era, symbolic AI. It's worth putting it directly side by side with statistical machine learning because the contrast is sharper than old versus new. It's actually 2 different philosophies of what reasoning even means. Symbolic AI encodes knowledge as explicit rules and logical relationships. If the cattle has a fever and loss of appetite, then consider East Coast fever. A human expert's knowledge written down directly, then executed step by step. It's transparent. You can always point to the exact rule that fired, but brittle, a combination of symptoms the expert never thought to write a rule for simply isn't handled at all. Statistical machine learning instead represents knowledge as probability and pattern, inferred from data and experience, rather than dictated by a human. Rather than a rule that says fever and loss of appetite means East Coast fever. A statistical model learns something more like across thousands of past cattle cases. This combination of symptoms correlated with East Coast fever 74% of the time. It's less transparent, there's no single rule you can point to, but far more flexible since it can handle combinations of symptoms no human ever explicitly anticipated, simply because the pattern showed up in the data. Say it back in plain words. Symbolic AI reasons by following rules a human wrote down. Statistical machine learning reasons by following patterns the data revealed. And that difference is the real story behind the shift from the 1950s into the 1980s and beyond. Machine learning itself isn't one single technique. It splits into distinct paradigms based on one simple question: how does the system learn? Supervised learning trains on labeled examples, pairs of an input, and the correct answer for that input, shown thousands of times, until the system learns to predict the correct answer on inputs it's never seen before. Predicting whether a river will flood based on historical rainfall records, trained on past flood events with known outcomes, is supervised learning. So is a disease classification system trained on animal symptoms already marked as healthy or sick. Several techniques fall under this umbrella. Regression predicts a continuous number, a crop yield, a rainfall amount, a livestock weight. Support vector machines, SVMs, find the boundary that best separates two categories with the widest possible margin on either side. Decision trees split data through a sequence of yes/no questions, like a traditional healer diagnosing an illness by asking a sequence of questions, arriving at a prediction at the end of the branch. And neural networks, the architecture underneath the RNN, CNN, and Transformer series covered elsewhere in this course, learn layered, increasingly complex patterns directly from raw data. All four are solving the same kind of problem. Learn from labeled examples, predict on new ones through very different internal mechanisms. Unsupervised learning trains on data with no correct answers attached at all. There's no answer key. The system's job is to find structure that was already hiding in the data without anyone telling it what to look for. K means clustering groups similar data points together, say grouping tree species by leaf shape or river flow patterns, without ever being told what the groups represent. It just finds that the data naturally separates into distinct clumps. Principal component analysis, PCA, finds the handful of directions in the data that carry the most information, compressing high-dimensional complexity down to its essential few dimensions, like distilling the behavior of an entire ecosystem into its most important indicators. Autoencoders, a compress, then reconstruct neural network, learn a compact representation of data with no labels required at all by trying to squeeze data down and then rebuild it as accurately as possible from that squeezed version. Real-world labeled data is often expensive and slow to produce, while unlabeled data is usually cheap and abundant. Semi-supervised learning splits the difference, trained primarily on a small labeled set, but also use a much larger pool of unlabeled data to learn the data's general structure, improving performance beyond what the small labeled set alone could achieve. This matters enormously in wildlife conservation. A team of ecologists might have a few hundred camera trap images that have been carefully labeled by a specialist: elephant, lion, giraffe, but thousands more unlabeled images sitting in their archive. Semi-supervised learning lets a model benefit from that much larger pool, rather than being limited to only the tiny labeled set. The same logic applies to crop disease detection. Confirmed disease cases are rare and expensive to verify in the field, but ordinary, unlabeled images of crops are abundant. And semi-supervised techniques let a model learn the general shape of unhealthy from that abundance, making rare disease patterns easier to spot by contrast. There is a fourth approach that sits slightly apart from these three: reinforcement learning. Here, the algorithm learns by interacting with an environment, receiving rewards for good actions and penalties for bad ones, but without ever being told the correct action directly. It explores, tries things, and gradually figures out which actions lead to the best cumulative reward over time. Think of a lioness cub learning to hunt. Its mother doesn't label every action as correct or incorrect. Instead, the cub stalks, pounces, and sometimes catches prey, reward, and sometimes misses, penalty. Over time, the cub learns which approach works best, staying downwind, moving slowly, timing the pounce, purely from the feedback of success or failure. That's reinforcement learning. It powers everything from game playing A is like AlphaGo to robotic control systems and autonomous vehicles. We'll cover this in full depth in a later video, but it's worth naming here because it's the third major pillar of machine learning alongside supervised and unsupervised. One analogy that ties all of this together: how a child learns. Here's a single analogy that captures every type covered so far, because a child is, in a very real sense, a learning system too. A mother giving supervised learning looks like pointing at an animal and saying, "That's a kudu," or pulling a child's hand back from a fire and saying, "Hot, don't touch." A direct label attached to a direct example, exactly the mechanism from earlier in this video. A mother giving reinforcement learning looks like praise when the child shares food and a consequence when they don't. No direct label saying sharing is correct, just a reward or a penalty after the fact, leaving the child to work out the underlying rule purely from that feedback. This is reinforcement learning in action, previewed here and covered in full depth later. And a huge amount of what a child learns is unsupervised. Nobody sits a toddler down and labels every tree by species or every animal by name. The child plays alone, sorts things by whatever pattern catches their attention, and discovers structure: round fruits roll, thorny bushes hurt, with no answer key at all. That's unsupervised learning running constantly alongside the more direct, supervised and reinforcement moments. Here's where the analogy gets genuinely useful, not just cute. As a child grows older, a parent has less and less direct control over exactly what that child ends up thinking. The child has generalized far beyond any single lesson a parent ever gave, combined thousands of small supervised corrections, reinforcement signals, and unsupervised discoveries into a worldview nobody explicitly programmed piece by piece. That's precisely what happens with a trained machine learning model too. Once training is complete, the model has generalized beyond any single training example into behavior the engineers who built it can't fully trace back to one specific cause. Training data shapes the outcome, for children and for machines. And here's the part worth sitting with. A child raised in the Okavango Delta, immersed daily in Setswana, the rhythms of the floodplains and the behavior of elephants and lions, trained in effect on Delta data, grows up thinking and feeling like a child of the Delta, not of the Kalahari. A child raised in the Namib Desert, trained on desert data, grows up thinking and feeling like a child of the desert, not of the Delta either. Neither outcome is about anything innate. It's a direct reflection of the data each child was raised on. Machine learning models work exactly the same way. A model trained overwhelmingly on one kind of data, say images from European forests, will reflect those forests' patterns, assumptions, and blind spots, not some neutral, universal truth about all trees everywhere. If you train a tree identification model on European data and deploy it in the Miombo woodlands of Zimbabwe, it will fail. Why? Because it never learned to recognize the patterns of African trees, the shape of a baobab, the texture of acacia bark, the way light falls on a jacaranda. It doesn't know how to see what it has never been shown. Say it back in plain words. A learner, human or machine, doesn't emerge from nowhere. It becomes a reflection of whatever data it was actually trained on, and changing that training data changes what the learner becomes. A model trained on Europe will see Europe. A model trained on Africa will see Africa. That single idea is one of the most important and most underappreciated facts about machine learning in practice. What is deep learning? Recall the neural networks mentioned under supervised learning a moment ago. Deep learning is machine learning using neural networks with many layers stacked on top of each other. Deep simply refers to that stack of layers, not to any deeper wisdom. Each layer transforms the data a little further, building up from simple patterns to increasingly complex, abstract ones. Exactly what our CNN series showed happening layer by layer, from simple edges in the earliest layers to whole object parts by the deepest ones. Think of it like an elephant recognizing a familiar watering hole from far away. The first layer detects simple things, shapes, colors, movement. The next layer combines those into more complex patterns. A large body, a trunk, the characteristic gait. The deepest layers put it all together and recognize that's an elephant I know. Deep learning works the same way, building up from simple features to complete understanding. The reason deep learning has driven the most visible breakthroughs since the 2010s comes back to part 1's three-part explanation. Enormous datasets to learn from, GPU hardware fast enough to train on them, and better techniques for training very large networks successfully. Take any one of those three away, and deep learning as we know it today simply doesn't work. Understanding the AI hierarchy. Here's a piece of vocabulary that trips people up constantly, and everything covered in this video sets it up perfectly. AI, machine learning, and deep learning are not three separate things. They're nested inside each other, each one a more specific, more specialized subset of the one before it. AI is the entire outer circle. Any system that perceives, reasons, learns, and acts, including old hand-coded symbolic systems that never learn from data at all. Machine learning is the circle inside it, specifically the AI systems that improve by learning from data and experience, as this whole video has covered: supervised, unsupervised, reinforcement, and semi-supervised. Deep learning is the smallest circle inside machine learning, specifically machine learning using the large, many-layered neural networks just described. Say it back in plain words. All deep learning is machine learning. All machine learning is AI. But not all AI is machine learning. Symbolic AI proves that. And not all machine learning is deep learning. K-means and decision trees prove that. Each step inward is more specific, more data-hungry, and in modern practice usually more powerful, but also less immediately interpretable than the step before it. Let's bring it all home. Layer 1. Machine learning is a subset of AI in which systems learn from data and experience rather than following hand-coded rules. The mechanism is a loop: guess, measure error, adjust, repeat, until the guesses become genuinely good. Layer 2. It comes in three main paradigms, depending on how it learns. Supervised learning with labeled examples, like a mother naming trees and animals for a child. Unsupervised learning with unlabeled data, like a child discovering patterns in the bush on their own. And reinforcement learning, which learns through trial and error, receiving rewards and penalties, like a lioness cub learning to hunt. Semi-supervised learning is a hybrid that combines labeled and unlabeled data within the supervised/unsupervised paradigm. Layer 3. Deep learning is simply machine learning at a particular scale. Many-layered neural networks requiring enormous data and compute capable of learning increasingly abstract patterns on their own. And the whole picture nests together cleanly. AI is the broadest category, machine learning sits inside it, and deep learning sits inside that. That's the map for how machines actually learn. Everything in our RNN, CNN, and Transformer series is deep learning, specifically the innermost circle, built on everything covered in this video. Thank you for watching this Artificial Intelligence Institute Africa AIIA video, brought to you by Ubuntu Guild. Subscribe to our AIIA YouTube channel and to Cognify.